So hello everyone, this is Aditya sir, and in today's class we'll be talking about, in today's video we'll be talking about some of the concepts of boundary layer, why this boundary layer is very important when we talk about fluid flows, and let me remind you that these are one of the most important topics when we talk about mechanical engineering, fluid engineering, hydraulics, and ocean engineering. Also, these play a very important role at many places. So let's try to understand what is boundary layer to begin with. Let's say the boundary layer is for the first time the boundary layer was observed by Ludwig Prandtl, Sir Ludwig Prandtl, one of the famous scientists that you will study about in your literature. So Ludwig Prandtl actually for the first time saw the boundary layer concept, and he did some manipulations to the Navier-Stokes equation and came up with the boundary layer equation for a steady flow. So what is basically a boundary layer? Let's try to understand that. Boundary layer is basically a very thin region, a very small region when fluid moves over the surface of a solid. Okay, so whenever a fluid moves over the surface of an object, a solid object, in the vicinity or very close to the surface of this solid, there is a very small layer which can be recognized when you zoom it out. Okay, so when the boundary layer is formed, this boundary layer becomes very important because the viscosity of a fluid plays a very important role in this region, as you can see here. So this region is basically a viscous region where viscosity plays an important role, and everywhere outside this region, because the viscosity effects are not so prominent and all the fluid are actually moving with the same speed, so we can say that the fluid is relatively at rest. There is no shear happening here. So this region is known as potential flow region, an ideal region. Okay, so generally when we divide a fluid flow which is moving over the object of the surface of an object, we divide this total flow into a potential region or ideal region which is in the neighborhood and immediately close to the surface of an object. Okay, so this surface is known as boundary layer. Why this is called boundary layer, what happens inside this boundary layer, that we will talk about. So an outside region is basically called a potential region. So viscosity effects are very prominent because we have seen that whenever a fluid moves, for example in a laminar flow, the fluid moves in the form of layers. So different layers of a fluid actually they move over through the air. Let's say when we talk about an air, it could be water also. So whenever this fluid actually passes over the surface of a solid, some of the fluid particles, actually every surface is rough in nature. Okay, so some of the particle which is close to the surface, they get stuck in this surface, they are not able to move over the surface. Now there are many advantages of this structure of these particles which are sticking on the surface. One advantage of this is because the particles in the lower surface, they get attached or somehow they stick to the surface, they make the fluid surface actually smooth, if you could see. So the neighboring particles could move easily over the surface of a fluid. That is how the nature behaves. The roughness of the surface makes the lowermost particle stick to the surface. So you can see here in this velocity profile, the velocity of this particular particle which is on the surface of a solid is actually 0, and this velocity keeps on increasing. So this is called velocity profile. Okay, so instantaneous picture, actually let's say the many fluid particles are moving over the surface, and at a particular station, at a particular point, if you take this particular cross section, there will be many fluid particles which will be arranged, let's say in this manner. So these fluid particles are actually moving over the surface of a solid. So let's say the lowermost particle will be attaching to the surface, the velocity will be 0. The above that surface will be moving with some higher velocity, and then it will be moving with even more higher velocity. Here you can see the profile to be parabolic. Here this velocity profile parabolic, but it varies from surface to surface. So what happens in this region is, here the picture is not visible. Whenever the fluid moves over the surface of a solid, the layer of a liquid which is in contact with the surface of a solid, it remains attached to the surface. Okay, that's why we called this condition, the fluid particles are not able to move over the surface or slip over the surface of a solid. So we call this region as no slip region. Okay, no slip condition, where the velocity goes to 0. This is called no slip condition. Above that, the velocity keeps on increasing, and to a point where it reaches close to a free stream velocity. That region, this region in which the velocity of a fluid actually changes from 0 on the surface of a solid to very close to the free stream velocity, or we generally called 0.99 times the free stream velocity. This region is called a boundary layer. Okay, so boundary layer has a different characteristics, which was first introduced by Ludwig Prandtl. Then let's try to see what actually, okay, so Reynolds number is another very important concept when we try to talk about the motion of a fluid. So first of all, Reynolds number, it is a dimensionless quantity. Now why Reynolds number is a dimensionless quantity? Because Reynolds number, it is the ratio of inertial forces. It is the ratio of here inertial forces to the viscous forces. So inertia has to do with mass. Okay, or inertia has to, when we talk about moving fluid, it has to do with momentum. Okay, so inertia forces and viscous forces, like you can see here. Now, what is the difference between inertia and viscous forces, and how a particular flow, a laminar flow, actually turns into a turbulent? Okay, that we will try to understand here. So inertia, let's take an example of a bike. For example, let's say you are riding a bike on the surface of a road. Okay, when the bike is running at a very slow pace, it will be attached, the tires will be attached to the surface, and it will be walking very smoothly. That is how the bike you will be driving. Okay, but so everything when the inertial forces are strong, let's say if the inertia forces are strong, the fluid layers, they follow an orderly pattern. They move from one place to another place in an organized, in an arranged manner. Okay, such a flow is actually called a laminar flow. You can see here the fluid particles, they are moving layer by layer. Okay, so layer laminae, this forms of, in two-dimensional form, it will form a layer which is also called a laminae. So because the fluid particles, they move in the form of two-dimensional layers, 2D layers, that's why it is called a laminar flow. In case of when the viscous forces are strong, very sorry, and when the inertia forces takes over, the speed increases. You can imagine that the speed of the bike increases. At high speed, what happens is the tires, they will try to leave the surface. When you go at a very high speed on a normal bike, the tires will be about to leave the surface at high speed. It will feel like the tires are running above the road surface. Okay, the friction will play very less important role because the tire is moving at a very high speed. So what happens in this case, when the fluid particles, it is moving at with very high speed, the particles, they lose their order, and they start moving randomly in an irregular pattern from one place to another place. So this leads to, when inertia forces are very strong, the flow becomes turbulent in nature. They have irregular pattern, they flow randomly, the particles move randomly in any direction. That is one of the most important thing. Okay, and Reynolds number is calculated using this formula, rho, V and D, where D is called characteristic length for pipe flow. When we talk about pipe flow, diameter becomes one of the major, you can say, characteristic, okay, to make the flow laminar or turbulent. And this is dynamic viscosity. So here the limits are written for laminar flow. So if the Reynolds number of the flow is less than 1000, then it remains laminar, and when the Reynolds number becomes greater than 2000, then the flow becomes turbulent. Now the question is, if this is 1000, this is 2000, what happens in between? If the Reynolds number is less than 1000, then laminar, and then again one more 1000 gap is there. So this 1000 Reynolds number, this much speed is required for the flow to become completely turbulent. That means if the Reynolds number increases beyond 1000, let's say in the Reynolds experiment, that also you will find out, in a pipe flow he did an experiment where you can see that the first layer, this one becomes turbulent, and then let's say as the speed increases, as the velocity keeps on increasing, the flow becomes more turbulent, and slowly this turbulence moves to different layers, and in order to become the complete flow to become turbulent, we have to achieve this Reynolds number, which is 2000. So this Reynolds number is very, very important. Between 1000 to 2000, the flow transitions from the laminar to turbulent region. The flow becomes completely unsteady beyond this 2000 limit. Then let's try to understand over a flat plate. So if you have a flat plate which is, let's say, a two-dimensional plate-like surface, okay, and here we are looking at side view of that plate, what actually happens to the flow parameters. So here when we try to calculate the Reynolds number, let's say this is the leading edge of the plate. So from the leading edge, the Reynolds, we calculate the distance of the plate where we are interested in calculating the station, the point where we are interested in calculating the flow Reynolds number. So as you can see from the picture here, from the image over here, initially the uniform flow, the undisturbed flow, the free stream flow, when it touches the surface of the plate, you can see the boundary layer starts coming into the picture. This region, in this region the flow remains laminar, but as you can see, the flow velocity will keep on changing. So as the flow moves to a larger length on the surface of this plate, the flow flow transitions to turbulence. Okay, the laminar flow changes to a turbulent flow, and this much length is required in order to flow to become completely turbulent. So this region we call it as transition region, where the flow actually transits. The flow transits from laminar to turbulent, which is very, very important idea. Okay, and in order to boundary layer to become stable, here you can see the boundary layer thickness which keeps on changing from 0.1 to actually 0.2. The thickness of this boundary layer keeps on changing. Generally when we talk about turbulent boundary layer, underneath, very close to the surface of the plate, there will be a sublayer, laminar sublayer, okay, which is sticking to the surface of the plate, and above which the flow is randomly moving from any direction. So here this is called viscous sublayer. Okay, this is a small layer which will remain attached to the surface, like I introduced you in very close. In the previous slide we have seen that in the close proximity, the particles, they sticks to the surface so that the fluid can move very easily. But when the flow starts moving very easily, the speed increases, and because of the presence of the surface, the flow start moving from viscous nature to the turbulent nature. There are many questions that you can ask. There could be a question, how because of the presence of the plate, flow becomes turbulent. Okay, what if the plate is not there, is it that the flow will become turbulent, or it will remain? So when we talk about free stream, when we talk about undisturbed flow, there is no we don't discuss about the boundary layer, because like I told you, the shear effect is actually zero in this region when all the particles are actually moving with the same speed. We call it relatively, the fluid to be relatively at rest. So here two regions. So you can see the thickness of the boundary layer, which is denoted by, let's say, delta, the thickness, or we can represent by any value. Here right now we are using the term which is used in the literature. So here the thickness of the turbulent layer, delta, actually changes from one point to another point. As the thickness of the boundary layer keeps on increasing, definitely with the increase in length, the boundary layer thickness actually increases. So if we want to calculate the Reynolds number at this station, at this point, let's say at point number 1, the Reynolds number could be calculated in this manner. So Reynolds number is equals to rho v, then you will have x, and then we will have here dynamic viscosity. We will also have the dynamic viscosity. Okay, so for example, let's say density of air is some 1.2 kg per meter cube, and then we have velocities, let's say some we will take it as 10 meter per second and 2 meter from the surface of the plate. So density is in kg per meter cube. Okay, so we need to remember that. And dynamic viscosity is, let's say, 0.01. What would be the Reynolds number at 2 meter if we want to check? So then it will be 1.2 into 10, 12 to the, this will become 24, and this 24 has to be multiplied with so 100. Actually 0.01 will be 100. Okay, so the Reynolds number here at this station, which is 2 meters from the leading edge of the plate, it will be around 2400. Okay, so that means because we know that if the Reynolds number is more than, so we know that if the Reynolds number is greater than 2000, the flow becomes turbulent. So this length scale typically it will lie somewhere here or within the turbulent region. Okay, because the Reynolds number is more than 2000, which is 2400. So boundary layer is very important phenomena which plays a very important role when you try to see a fluid moving over a cylinder or the surface of a solid object. We encounter these kind of a situation which is interesting to see. Then coming to the, like we have discussed, what is boundary layer thickness? Boundary layer thickness is the thickness of the boundary layer. Okay, and so the distance, technically we define it as the distance which is measured perpendicular from the surface of a solid. So the distance, perpendicular distance measured from the surface of a solid, surface where the velocity from the at the surface velocity is 0, and at a 0 point, like we have mentioned here, at a distance where the velocity becomes 0.99 times the free stream velocity, this is called boundary layer thickness. Okay, so most importantly here you can see that boundary layer is a function of x. Here the thickness of the boundary layer is actually changing along with the distance from the leading edge, which is given by the value of x. Then there are three important things that we consider when we understand when we try to investigate the boundary layer in detail. So there is something called displacement thickness, there is something called momentum thickness, and another term which is energy thickness. So what is this displacement thickness, what is this momentum thickness, and what is this energy thickness? So displacement thickness has to be, it is related to the loss of mass flow. Okay, so because of the change, what happens, so technically when mass flow rate is given in this manner, uv into a, that is how we calculate mass flow rate. Now because of the presence of the plate surface, because the velocity of the particles, velocity of the fluid particles here, they have decreased. Initially the velocities were this much, which is denoted by this vector. Now the velocity has actually decreased. Because the velocity has decreased, that means definitely there is loss of mass flow rate in this particular section, let's say for this particular length. Okay, so in order to gain the same mass flow rate as that of the free stream flow, how much distance we need to shift this boundary layer in the region of potential flow. So here we have free stream velocity, how much more we have to displace it in order to calculate. So we calculate loss of mass from this particular formula, and the displacement thickness, which covers the loss of mass, which calculates the loss of mass in order to make the mass comparable to the initially free stream velocity, how much we have to displace this thickness. So this in order to get the initial mass flow rate, now the first question we can ask is why we are doing this. So this I will leave up to you to figure out, and we will talk about in the next class. So delta star, this is how we calculate 1 minus u by free stream velocity. The further calculations we can check in the book, any book which is related to fluid mechanics. So this is called a displacement thickness. Another, when we talk about momentum loss, so what is the loss of momentum, that also we are supposed to calculate. And then here again we have a formula for this momentum. Momentum is nothing but mass flow rate into velocity. So here area is actually we are calculating in terms of width of this particular plate we will take as 1 unit, and then we multiply with this particular thickness. Okay, so that will give the entire area which is encountering this change in height of the boundary layer. So the loss of momentum, generally in many books you will see it could be calculated in terms, it is written in terms of by representing it by theta. So u by u infinity 1 minus u by u infinity dy, and then again this is energy thickness. So what is the loss of energy because of the presence of this horizontal plate? What is the loss of energy in this particular region, and in order to recover that energy, by how much distance we need to shift this boundary layer, that's called energy thickness. So that's all for today's class. In coming classes we will solve some numericals also. You can contact me at the given mail ID and phone numbers. Thank you very much. Have a very